So now we come to our last method that we've emphasized this semester. In Chapter 5, we spent the last week learning the finite element method. So now we're on the heat equation, and we're going to look at how the finite element method, just like the spectral method, is useful in studying the heat equation. So the first, remember there are three phases to that. The first was to write the PDE in weak form. And by weak form, we take the PDE and we multiply everything by V and integrate. That's what we mean by the weak form. And we do the same thing that we did last time, where when we had minus UXX was the PDE, we integrated by parts. And so when you integrate by parts, a derivative comes off of U and goes onto V. And that also switches the sign. And so that's how we get the weak form of the PDE. And remember, this part, these two terms, covering this up, that is the same as the Laplace equation, and the same thing that we got as the weak form for the Laplace equation. So for the heat equation, what changes is we have this extra term here that has the U sub T, the derivative with respect to T, times V. So we'll see how that all works out. Remember, the next phase of the finite element method is that we used the Galerkin method, and there's a projection theorem argument that shows that if we represent U in terms of a basis and only take a finite number of them, we can do this in a way that gives us the best approximation to the true solution U. And then the final part is actually picking the basis functions. And in this class, we pick piecewise linear polynomials. And in fact, we pick them so that each basis function is 1 at that node point and 0 at all the others. And we called these tent functions. So all of this is the same, except we have this extra term. And so when we substitute in for U into that equation, and when we use phi I as the V, then phi I as the V shows up in every single place, and we integrated by parts, and so phi I has a prime on it, and that becomes a plus. And now for U, we have phi J, and then UJ. And notice we do this for heat equation, where we let these coefficients depend on T. Just like with the spectral method, we let the Fourier coefficients depend on T. And so when we do that, we get these three terms, and the integrals are in space and have only the basis functions in them. And because we choose our basis functions to be these tent functions, nice, linear, and piecewise, then we can actually evaluate each one of these integrals. And it's for each pair, ij, each ij pair, we integrate here with no derivatives, which means we're actually integrating a product of linear functions. There might be up to x squared when we do these integrals. Here, we're integrating the derivatives. The derivatives of linear functions are the slopes. And so here we're integrating constant functions for each pair, for each I and j. And here we take the f, the function f, and we are multiplying f by phi I to integrate. And so since those integrals only have x in them, except for this one on the right-hand side, it can depend on t, we can compute these as matrices, an mij and a kij. And here's what we like about the finite element method. That is, because we define these tent functions that are 0 in so many places, when they're overlapping, we get two non-zero things multiplied together, and so we actually have to compute that integral. But if we've got a bunch of different points in our domain, then most of those tent functions do not overlap, meaning one of them, or both, is 0 in most places. And so when we compute these matrices, we're actually just going to get a lot of zeros. And so we don't have to do any actual work in computing zeros. And so that's why we like this finite element method, this Galerkin method with piecewise polynomials, or in this, I guess, piecewise linear basis functions. And when these matrices have so many zeros, remember we called those sparse matrices. And so Kij is the same matrix that we computed before in chapter 5 that was called the stiffness matrix, and it's where we integrated the slopes or the constants. This is the same kind of thing that we computed before, except now there's some t dependence. We called that the forcing vector. So the new one that we're computing, the one that does not have the derivatives of the basis functions, meaning that they are a product of linear functions that we're integrating, this matrix we call the mass matrix. So when we end up with what we end up with here, before we ended up with just Ku equals F, and if U is stored as a list of coefficients as a vector, and this is a matrix times a vector is another vector, we could solve that system of linear algebraic equations by row reduction. Here we have this U dot. Because the derivative was with respect to t, the derivative comes out of the integral, just like the u that depends on t comes out of the integral. So now this is a system of linear first-order ODEs. So this first-order linear ODEs, this is like chapter 7 of last semester, where there's a matrix times a vector, like an mu dot. And then there's also this linear term, the 0th order term, and then the non-homogeneous term. So we can go back to some of those techniques to solve these. The other thing, though, is when we have these large matrices like this with mostly zeros, computers are very good at solving equations like these. And so usually where we go to solve these is on a computer. Notice on your homework problem, it asks you to write these. It actually does not ask you to solve these. If you want to solve these, just come and see me when I'm back from paternity leave, and I'd be happy to help you see how to solve these. It's a lot of fun.